Good evening, everyone. My name is Dustin Bracey, and I'm going to walk us through a time series analysis on COVID-19 data in Louisiana. All right, so let's talk about positivity rate. Positivity rate has been in the news quite a bit, and it's the ratio of tests actually positive over the total number of tests. This is a new metric because the total number of positive cases is getting bigger and bigger every day. The WHO has come out with 5% is a rule of thumb, where if the positivity rate is greater than 5%, it indicates that really high transmission rates or maybe a potential shortage of tests. We're going to see that a little bit in the realizations that I show you on the next slide. The really big peak that you see at the beginning was because we were testing only the people that we were pretty sure had COVID-19 coronavirus, and so there was an unusually high number of positive tests because of that. They were in short supply. So it improves on simply measuring the total number of cases just for people who have tested positive multiple times. The people that need to go back to work and they're testing 3 or 4 times before they get a negative result so they can go back to work. Ideally, we would measure the total number of people who have tested positive over the number of times that same person was tested, but privacy laws, HIPAA, kind of prevents that from becoming a reality for us. So here's the positivity rate comparison with the total number of new cases each day. And you can see the positivity rate looks a little more normalized. There's a little bit less variance in it than the total number of new cases, because that varies wildly with the number of cases that are in supply. All right, so let's jump right into it. This is a univariate stationarity analysis of Louisiana. And so a stationary time series model would indicate that this realization right here is going to return to some sort of mean. So there's going to be some sort of mean here. And this is telling me a lot. So this autocorrelation, slowly damping sinusoidal autocorrelations, and this really strong peak here at 0.14 and an echo here maybe at 0.28 indicate that this is probably a seasonal model. This is an overfit table that I've generated for an AR-15 on this data set. And you can see that if we look at a factor table for 1 minus b to the 7th, which is weekly data, you can see that these factors are all present in this data. And they have these roots are really strong, really near the unit circle here. And so I think this model is going to predict really well for us. So let's take a look. So this is the actual data. This is the same slide I just showed you. This is a generated weekly AR-15 model. You can see, look at the autocorrelations. They're pretty similar, slowly damping, sinusoidal. The frequency window, it's got that peak at 0.14 and 0.28, a little bit of a high peak here at 0.45, but I think this is going to predict pretty well for us. So here's a 7-day forecast with that AR-15 weekly model, and this is a 90-day forecast. You can see the 7-day cyclic behavior that's generated by that seasonal component. So here's an NN4. This is a neural network multi-layer perceptron, and it performs pretty well. It looks like almost like an AR2, like it's got a slowly damping towards some mean that it thinks the data is gonna come back to normal here. And so it actually performs fairly well in both cases. All right, so let's look at the U.S. data. This U.S. data, again, I don't see the strong peaks like I did in the Louisiana data. So this indicates that maybe this could be a stationary model. And I'm going to difference it. I difference it once here, and the sample autocorrelations of that difference data, once I apply that filter to remove out these big trends and just leave me with the cyclic behavior, that looks a lot like white noise to me. So I think I'm going to model this as a stationary model, and this is an autocorrelation, a partial autocorrelation plots that are showing me I would only expect to see maybe one of these in 20 observations that are outside of this band, and that looks about right. All right, so here's, again, actual data, the same plot I just showed you, and this is a generated AR91. Look at this realization looks okay. This frequency window looks maybe a little bit too high of a peak here at 0.1, but the slowly damping lag autocorrelations here, I think this is going to be another good fit. So look at the short-term forecast, looks really good. This is a really small ASE, but again, this is the textbook example of extrapolating. When we're trying to forecast 90 days out, this model is maybe not the right one. So it's forecasting this trend to go up when in fact it's going down. This is almost worst case scenario here. So you got the ASE here is 0.01, which is pretty high compared to by an order of 10 on the 7-day forecast. The NN4 has the same problem. It's got a pretty decent, these predictions aren't terrible, could be better. But the seasonal, it's forecasting this trend here, and it correctly captures this downward trend. But again, because it's extrapolating, it just says, okay, I'm going to just forecast this trend to continue, and then we lose some scores here in the future. All right, so multivariate component. I gathered weather data and gathering events, what I thought was going to be significant to impact us towards COVID-19 transmission. The U.S. I couldn't bring in weather data because it doesn't make sense if it's not regionalized. So you can see once we bring in that multivariate analysis, the VAR model is actually performing really, really, really well. And this is a rolling window ASE, a visualization of the whole data set, and then 7-day plots. I've got 6 plots in here that use a month of training data and forecast the next 7 days, and you can see it's following this trend really, really closely. US data, I use NN4 in this example, and it's forecasting, it looks like a linear trend here. So it's capturing the trend correctly, but it's got a little bit too strong of a linear pattern, with the exception of this last one here. But again, see the 0.00008 is a really good mean ASE. And it actually tops out as our best performing model, or one of the best here. And the AR model and the AR91 are actually what I'm going to use as our final selection here. The weekly AR15 that I showed you and the AR91, a little bit more simple, and I think they forecast really, really well in the short term and in the long term. They're very balanced models, and I think they're going to perform very well for us in the future. So let's see what it looks like. This is straight into the future with no data, and again, this cuts off on November 11th. So now that we're into December, we can go back and look and see how well these predicted. But you can see Louisiana is predicted to kind of continue that cyclical trend, and it's going to go up a little bit. In U.S., the data looks like it's kind of exploding, which might explain some of the new restrictions that the CDC and our government leadership have been applying. All right, so that's it. I encourage you all, please check out my my R Markdown and my code. I have a lot more plots that I just don't have time to show you today. And let me know if you have any questions. Thank you.